Hello, everyone. I'm Xuejun Chang from the University of Glasgow. I'm delighted to be here to present our paper called Neuropacity Quality Estimation for Static Pruning, a joint work with Debabrata, Mishra, Craig Macdonald, and MacAvaney. To illustrate our motivations, we are going to start by looking at some example passages from MS Macro version 2. You might need seconds to read it. Well, what information needs this passage could satisfy? It could be guitar for sale. It could be where is the Stratocaster guitar manufactured. It could be, and so on. So let's see another passages on the right side. Let's have a quick look at it. Reading this passage, it's quite difficult to think of queries that this passage might answer. Further, even the queries we might think of, it's actually not a good answer. Now, in our work, we call the left passage high quality because it provides valuable information and satisfies reasonable information needs. On the other hand, we consider the right passage low quality, since it shows no valuable or little information and could only satisfy odd information needs. Probably, this passage is not a good result for any reasonable query. Here, we are talking about the notion of quality that is independent of any query. So far, you have understood what the passage quality means. We are here to raise the question, can we predict the passage quality before indexing? If we can do so, then lower quality passages could be removed or pruned from the corpus without affecting retrieval effectiveness. Consequently, we can remain fewer indexed passages that would lead to faster retrieval, lower storage costs, and so on. Since our work is a neuropacity quality estimation, let's see how it differs from existing methods. The first existing method is spam filtering, which identifies documents that have been purposefully crafted to be highly ranked. However, our goals are not limited to this specific setting. Documents can be lower quality for a variety of reasons, such as bad segmentation, lower information density, and so on. The second one is term-centric static pruning, which removes post-list items that isn't important to a document. On the other hand, we remove the entire document. The last one is the lexical quality estimation, which uses the lexical heuristics to remove documents, such as information to noise ratio, unigram perplexity. In comparison, our neural model should be able to learn a more refined and accurate estimate than lexical signals. After discussing passage quality estimators, let's see what a static pruning index pipeline for passage quality looks like. Given a passage corpus, we apply for quality estimator to score passages as either high quality or lower quality. Then we prune these passages based on their scores. After that, we can apply any indexer on the pruned corpus, such as the dense or lexical indexer. This means that we can apply for our passage quality pruning to any indexer. Actually, we can express such index pipeline in Pythagorean notation like this. However, how to implement a quality estimator? Let's see some existing lexical quality estimators. One is the information to noise ratio. That is the proportion of unique terms in a document. The red background passage we have already seen has an item of 0.8, which would indicate it's a good quality passage. However, as we discussed before, it's probably not that useful. The second method is the collection document distance, which measures the KL divergence between document and collection language model. Actually, this is not an ideal quality measurement just because a document that's typically distant from the rest of the collection doesn't mean low quality. Apart from lexical estimators, how else might we measure document quality? Here we explored several neural quality baselines. The first baseline is language model perplexity, which means documents may be of low quality if they are seen as unlikely to a neural language model. Perplexity measures the inverse likelihood that language model would generate a sequence of tokens. The second baseline is dense vector magnitude. We observe that dense biencoders may learn to encode lower quality passages as smaller vectors. Similarly, in the epic land sparse retrieval approach, there is a land latent document quality signals by scaling its vector magnitude, which may also be indicative of document quality. That is actually the size of encoded passages. Now we start to introduce our supervised neural passage quality estimator that is fairly simple. Consider monotone 5. At the training time, we show it human annotated relevance data that consists of query and relevant labels. Our key idea is what would happen if we just simply didn't tell the model the query. This would make our passage quality estimator. Given a passage, is it likely to be relevant to any query? Therefore, we are dropping query to the model. So when we introduced our neural quality model, we now seek to find out how our models perform when pruning the corpus. In our experiment, we used the mathematical corpus, the dev query set, and evaluated using reciprocal rank at 10 over a variety of pipelines to compare the pruned percentage within 70% among different models, as well as performed the tooth equivalence test to the effectiveness of the fully unpruned corpus. We used the lower bound threshold of 5% and arbitrarily larger upper bound, since improved effectiveness is a desirable side effect. To report our results, the percentage proved is on the x-axis and the reciprocal rank is on the y-axis. The no pruning baseline is shown as the horizontal line. Our random pruning baseline, which randomly sample a given percentage of passages to remove, quickly decreased the effectiveness, and only 5% proved does it show equivalent effectiveness. Let's see the performance of information to noise ratio. It can prove 15% of the corpus while maintaining equivalent effectiveness. A few points are even better than the baseline, while CDD can only remove 5%. Now we add curves for the neural signals. The result shows that using language model perplexity, magnitude of TESB and episodic quality scores aren't better than ITN. However, our supervised training model, QT5 base, in blue, can prove up to 60% of the corpus while maintaining equivalent effectiveness. So far, I have been showing you results for BM25. Let's see how it performs in a re-ranking setting using BM25 and the monoelectra. Again, our supervised model is much better than all the other qualitative models, pruning 30% of the corpus. It performs almost identical curves for TSB density retrieval and split land sparse retrieval at 30%. As you might consider, passing every passage through T5 base before indexing might be expensive. So we tried fine-tuning smaller models, such as T5 tiny, which still allows 35% to be proved while maintaining equivalent effectiveness. However, we wonder, is the quality estimation worth the cost when indexing? The short answer is yes. It can reduce compute as long as the cost of quality estimation is less than that of encoding and pruning percentage is large enough. The chart shows the throughput in milliseconds per passage. We observe that QT5 tiny and TSB encoder can reduce index cost when pruning is more than 13%. In our paper, we proposed the concept of break-even to measure how much percentage of corpus that need to be pruned to offset this pruning cost. This is because we can check the quality of many passages in the time it takes to encode one passage on the TSB indexer. Finally, to verify whether our model is still effective on a bigger offset or a different domain, we tested on MS Macro version 2 and the track DL 2021-2022, as well as different domain code 19 with track COVID, evaluated using NDCDG at 10. The results showed consistent pruning effectiveness. Our QT5 tiny has shown to be effective. For MS Macro version 2 setting, it can prove 20% at least for TSB and the re-ranking pipeline without reduced effectiveness. While for code 19, the model can prove more than 35%. In summary, we first proposed a novel quality estimation approach without considering any query. It outperformed other heuristic paradigms since no complex heuristic steps needed. Secondly, our model can remove entire passages and thus prove at least 20% of corpus consistently, outperforming existing estimators. Future work could investigate to set the pruning thresholds and application of datasets without predefined passage segmentation. Lastly, we argue that it's not unnecessary to index all of passages because not all of them provide valuable information. Neural model can be more intelligent and learn what to index. Thanks for your attention.